Welcome back to the deep dive. We have a really fascinating set of papers on the desk today.
They really do.
And honestly, the implications are a little mind-bending. We're looking at a collaboration between Stanford, Berkeley, UCSD, and NVIDIA that
Well, it challenges one of the most fundamental rules of AI as we know it.
it absolutely does. It questions this whole idea that a model has to be finished before you can use it.
Yeah,
The assumption that learning, just stops once the software is shipped.
right. And the source material, this paper, End-to-End Test Time Training for Long Context, it starts with a concept that feels so human. It's this analogy about how we learn.
It's the perfect place to start because it just highlights the inefficiency of our current tech. I want you to try a thought experiment they propose.
Okay.
Think back to college. Maybe your very first lecture in a really dense subject, like Intro to Stats or something.
Oh, man. I'm thinking of a philosophy of logic class. Total nightmare. I spent half the time just trying to figure out what the words meant. Perfect example. So, do you remember the instructor's exact first word? Like, can you literally replay the audio in your head right now?
Not a chance. No way. I couldn't quote a single full sentence from that whole semester, let alone the first word.
Right. But did you walk away with the intuition? Did your brain, did it update its mental model of how logic works?
Oh, definitely. Yeah. I couldn't recite the textbook, but I understood the concepts. The software in my brain was updated. I was different after the class.
And that distinction between recording the lecture and learning from it, that's the core problem in AI today. Humans compress experience. We change our internal wiring.
But AI models don't do that. I thought the whole point of machine learning was, well, learning.
It is, but only during training. The current kings of the hill, transformers, the T, and GPT, they're designed for what we call lossless recall. They're hoarders.
Hoarders, that's a strong word.
It fits, though. If a transformer wants to generate the next word, it basically has to look back at every single word that came before it. It keeps this perfect, high-fidelity copy of the entire context in its working memory.
So if I feed it a 500-page book and ask a question, it's actively juggling all 500 pages in its head just to answer.
It hasn't summarized the first 499 pages.
Yeah.
It's keeping them all active. And that's the problem. It's the quadratic cost.
Okay. Break that down for me. Quadratic cost.
Well, think of it this way. If you double the length of the book, it's not twice as hard to process. It's 4 times harder.
Wow.
Triple the length, it's 9 times harder. The memory, the compute, it just explodes.
Which explains why my API bill goes up with long documents and why chatbots get slower the longer the conversation goes.
Exactly. So that's the hoarder approach.
But there are other ways, right? We've talked about RNNs.
Right. Recurrent neural networks, or the newer ones like Mamba 2, they're the minimalists. They have a constant cost, meaning the effort to generate the next word is the same, whether they've read 1 page or 10,000 pages. They're incredibly fast.
That sounds perfect. So why aren't we just using those? What's the catch?
They're forgetful. They process a word, they update a tiny little summary, and then they throw the word away. As the book gets longer, that summary gets muddier, they lose the plot. By chapter 3, they've forgotten who the main character is.
So that's the trade-off we've been stuck with. You either get the genius hoarder who's slow and expensive, or the fast minimalist with the memory of a goldfish.
Yeah, that is the dichotomy that has defined the last few years, until this paper.
And that brings us to our deep dive. This paper proposes a third way, a way to get the quality of the transformer with the speed of the RNN. And the method is called test time training.
Yeah.
The name itself is kind of weird, isn't it?
It sounds like a paradox because, traditionally you have 2 phases. Training. You spend months and millions of dollars teaching the model. Then inference. You freeze it, ship it, and it just answers questions. It never learns anything new.
It's a frozen brain, read only.
Correct. But test time training, or TTT, asks, what if inference was actually a mini training session? What if the model could actually train itself on your prompt while it's reading it?
Whoa, okay, let's unpack that. So as I'm feeding it that 500-page book, it's not just looking at the words. It's rewriting its own brain.
That's the core idea. It is physically updating its internal weights, its synaptic connections, if you will, based on the specific document you're feeding it.
That's the human analogy again.
Exactly. A transformer is like someone trying to memorize a textbook photographically. TTT is like someone reading it with a highlighter and a pen, taking notes in the margins.
Changing the book itself.
Right. By the time they finish the book, the model is physically different. Yeah. It's customized to your specific problem.
Okay, but how does it know how to update itself? I mean, usually you need a teacher, right? To tell you if you're right or wrong.
It uses the exact same trick they used to train these models in the first place. Next token prediction. As it reads your input, it covers up the next word and tries to guess it.
Like a game. The cat sat on the... and it guesses Matt.
Exactly.
Oh.
And if it guesses roof, but the book says Matt, it calculates the error, the loss, and uses that error to update its weights right then and there.
So it's self-correcting in real time.
By the time it gets to the end of the novel, it has trained on that novel thousands of times.
I see a huge risk here, though. If I'm messing with the model's brain, couldn't I break it? If I feed it a bunch of medical journals, will it forget how to speak normal English?
That is the biggest risk. It's what we call catastrophic forgetting, and that's where the end-to-end part of the title comes in. They structure this with two loops, an inner loop and an outer loop.
Okay, inner and outer.
The inner loop is what we just described. You, the user, feed it data, it updates its weights. That's the test time part.
Got it. And the outer loop?
The outer loop happens back at the factory. This is meta-learning. They didn't just train the model to know facts. They trained the model to be good at being trained.
Wait, run that by me again. Trained to be good at being trained.
Think of it like this. They optimize the starting weights of the model so that when the inner loop starts messing with them, the updates are efficient and stable. It's learning to learn.
So they built a brain that's designed to be malleable in a very specific, safe way.
Exactly.
It's a slate that is primed to be written on. It knows how to take notes without ruining the book.
That's a great way to put it.
So let's look under the hood. Is this a totally new architecture? A new kind of neuron?
Surprisingly, no.
Oh.
It's mostly a standard transformer. But they made a crucial swap. They took out that expensive, hoarding full attention mechanism and replaced it with sliding window attention.
Sliding window. Okay, that sounds like it's looking through a paper towel tube. It can only see what's right in front of it.
That's a fair comparison. It has a short-term memory. It only looks at, say, the last few thousand words perfectly.
But wait, if it only sees the last few pages, aren't we back to the goldfish problem? How does it remember the start of the book?
And that's the magic trick. It uses the sliding window for the immediate stuff grammar, sentence structure. But for the long-term context,
The plot, the themes,
it relies on the weights it updated.
the notes in the margins.
Yes, it doesn't need to remember the first chapter in a cache because it has become the first chapter. The knowledge is compressed into the processor itself.
That is a wild concept. Now,
Yeah.
practically, rewriting a neural network sounds computationally heavy. Are they updating the entire brain?
No, that would be way too slow. They only update the MLP layers.
The MLPs, quick definition.
Multi-layer perceptrons. Think of a transformer block as two parts. Attention figures out how words relate, and the MLP processes the information. It's the thinking block.
So they only update the thinking blocks.
And even then, they're selective. Only the MLPs in the last quarter of the model's layers.
Why just the end?
It's a trade-off.
Yeah.
Updating the deep early layers is just. It's too computationally expensive. By targeting the later layers, they get most of the benefit of adaptation without the massive drag.
And what about my fear of it forgetting English? How do they stop that?
They essentially split the brain in those blocks. They keep a second static MLP layer right next to the changing one,
Like a backup drive.
more like a sidecar. One path is flexible and learning from your document. The other path is frozen and holds on to all the pre-trained knowledge, grammar, world facts, all that stuff. The model combines both.
Smart. It's like having a notebook for the class, but keeping the textbook on the desk for reference.
That's it. And one final detail that makes it work, mini batches. Instead of updating after every single word, which would be chaotic,
Jittery.
it reads a chunk, say 1,000 tokens, digests it, calculates the update, changes its weights, and then moves on.
It consumes the data in bytes.
And that stabilizes the whole learning process.
Okay, so the theory sounds solid, but the big question, does it actually work?
This is where the paper just drops the mic. They have this graph, figure 1. It plots loss, which is basically how confused the model is against context length.
Okay, and we want the confusion to go down as it reads more.
Exactly. For the full attention transformer, the expensive hoarder, the line goes down. It gets smarter, which is what we want.
That's the gold standard.
But for the fast models, the RNNs, the Mamba crowd, their line stays flat or even goes up. They get overwhelmed.
They get worse.
They get worse. But the TTT model, its line, behaves exactly like the transformer. It goes down. It matches the quality of the expensive models perfectly. They literally turn the worst line into the best.
Okay, so it's smart, but is it fast? Did they hit the RNN speed goal?
They did. In terms of latency, it behaves like an RNN. It has constant speed.
Put that in real numbers for me.
For context of 128,000 tokens, that's a very long book.
Yeah.
TTT is 2.7 times faster than a transformer on an H100 GPU.
2.7 times faster. That's the difference between a user waiting 10 seconds versus, like, 3. That's a huge deal.
And that gap widens. At 1,000,000 tokens, the transformer would probably choke, while the TTT model just keeps chugging along at the same pace.
I saw one other result that seemed weird, the early token advantage. It's actually better at the beginning of the document, too.
This is a subtle but powerful point. A standard frozen model is a generalist. It has to be ready for Shakespeare or Python code or a recipe for lasagna.
Right.
But the TTT model, the moment it reads the first 1,000 tokens of your document, it starts to specialize. It stops trying to be a generalist and becomes an expert in your document.
So it stops trying to be good at everything and focuses on just this thing.
It essentially cheats.
Yeah.
It changes the test to suit what it's already learned from the prompt. That's why it outperforms even the big models on those early sections.
Okay, I am waiting for the other shoe to drop. This sounds too good to be true. Faster, smarter, adaptable. What's the catch? What's the kryptonite here?
There's always a trade-off. In this case, it's the difference between compression and recall.
Explain.
The full attention transformer, because it hoards everything, has perfect recall. If you ask it to find a specific random password mentioned once on page 50 of a 500-page manual, it can find it instantly. That's the needle in a haystack test.
And TTT.
TTT fails this test.
Ouch. Wow.
Because it compressed page 50 into its weights. It remembers the logic of page 50, the vibe, the structure, but it didn't photograph the random string of numbers, just like you or me.
Right. I couldn't quote the 47th sentence of this deep dive later. I'd paraphrase it.
Exactly. You would compress it. TTT is more human-like in its flaws. It understands the book, but it can't recite it verbatim.
So if I'm a lawyer looking for a specific clause, I might still want the old school model. But if I want a summary of the legal arguments, TTT is better.
Precisely. It's an intuition machine, not a database.
What about building them? Is it harder to train a model that learns how to learn?
Much harder.
Yeah.
Because you have that outer loop optimizing the inner loop, you're dealing with some nasty math called gradients of gradients.
Sounds painful.
It's computationally heavy. Training is about 3.4 times slower than a standard model. But the argument is you pay that cost once at the factory, so the user gets the speed benefit forever.
So let's zoom out. What does this actually mean for you, the person listening right now?
For you, this is about the user experience of AI. We're hitting a wall where AI is getting smarter, but also slower. This tech promises a future where you can drop a massive code base or a year's worth of financial filings into a model.
And get an instant answer. No watching the cursor blink for a minute.
Instant and conceptually deep. And because it runs on standard hardware H100s, it's actually deployable. It doesn't need some exotic new chip.
The paper also touched on something that I think is the most sci-fi part of all, decoding. It's not just for reading, it can write too.
This is where the self-training idea gets really wild. It's not just for reading your prompt, we call prefill, but also for writing. Imagine the model is writing a novel.
Okay.
As it generates the first chapter, it can use that text, which it just created, to train itself before writing the second chapter.
It's learning from its own train of thought.
Yes. It effectively thinks, updates its brain based on that thought, and then uses the new updated brain to think the next thought.
That seems like it would solve the problem where AI writing tends to lose the plot after a few pages.
That's the hope. It maintains the state of the story not just in memory, but in the actual neural connections of the model itself. It literally becomes the storyteller.
It's evolving as it speaks, which leads to the final thought the researchers left us with. It's a bit of a provocation.
It is, and this is the idea that will stick with me. If the model updates its weights based on what it reads, and it can generate its own text to train on, what happens if we let it pause before answering a hard question?
Pause. Like, hang on, let me think about that.
Exactly. What if, when you ask a complex physics problem, it doesn't answer immediately? What if it generates a bunch of internal monologue, its own thoughts, not to show you, but just to update its own weights?
It's doing push-ups before the game, prepping its brain for my specific question.
It could program itself into a state where it's smarter about your specific problem before it gives you the final answer.
That blurs the line completely. The training phase never really ends.
The line between training and inference is dissolving. It suggests a future where AI isn't a static product. It's a process that is physically evolving with every single interaction you have with it.
A constantly evolving process. That is both exciting and, frankly, a little intimidating. But that's why we do these deep dives.
Always a pleasure.
A huge thank you to the researchers at Stanford, Berkeley, UCSD, Astera, and NVIDIA. And thank you for listening.
Keep learning.
See you next time.